Okay. Okay. Yeah. Good morning, everyone. Today, I'm pleased to welcome Dr. Sean Lawley, Associate Professor of Mathematics at Utah. Professor Lawley received his PhD in mathematics from Duke University in 2014 and has since been a leading researcher in applied math and mathematical biology. His work mainly focusing on stochastic process, diffusion, and first passage time theory with application ranging from cellular dynamics to biomedical systems such as ovarian aging and drug transport. He's a recipient of several prestigious awards, including the Science Life Science Early Career Prize, and has led multiple NSF-funded projects. Uh, and his research so far provides very fundamental insight into how stochastic governs a complex biological system. So please welcome Dr. Lowley.
Well, thank you. Thanks so much for the invitation. Thank you for the kind introduction. I'm glad to be able to meet some of the people on the call already. Um, I really feel honored to be able to give this talk here. I've admired the this research institute, IBS, for some time, so I feel very honored to do this. So
Well,
the title of my talk, as you can see on the slide, is Stochastics in Medicine, and I'm going to talk about two very different projects. Advance the slide.
mhm.
The two different projects are one is in ovarian aging and how that relates to menopause. And then the second project is in medication adherence, which is sort of related to missing drug doses. But if here at this at the top of the slide, this is the big idea of the whole talk. And so if you don't get anything else from the talk, I'd like you to get this one point, and it's this point here on the slide that stochastic modeling is a uniquely powerful tool to address questions in physiology and medicine. So that's what I want to spend the next a bit of time together arguing. Okay, so I want to argue and make that point that mathematical modeling and specifically stochastic modeling is a really powerful and in fact uniquely powerful tool to answer questions in physiology and medicine. And the way that I want to argue that claim is through two different projects. And the first project is about ovarian aging, and the second about medication adherence. And they're very different projects, but they're united by this one key idea that stochastic modeling is really useful to answer these questions. And I'm going to try to hopefully make that point that other ways of answering questions in medicine. You think about clinical trials. Um, I hope to make the point that those types of methods are not so uh, are hard to apply in these particular areas, and math really is the a key tool. So let me jump into it. The first project in ovarian aging. This is a collaboration with a number of other researchers. I'll highlight here. The left of the slide is Joshua Johnson. He's an ovarian biologist in the University of Colorado School of Medicine. And some of this work is also with Jay Emerson. He's a statistician at Yale. And then a big driver of the project I'm going to talk about today is Kutluk Oktay, who's a surgeon at the Yale School of Medicine. And some of this work is also a collaboration with Nanette and Mary, who are both at the University of Colorado. And I want to thank the National Science Foundation for funding. Let me jump right into it. I want to tell you about ovarian tissue cryopreservation. So what is that? Well, rather than tell you about the this medical procedure in general, I'll tell you about it in a specific use case.
Mm.
So here I have on the slide some pictures of Elise Starling when she was a child, and she battled leukemia three times as a child. When she was 3 years old, and then again when she was eight, and then again when she was 15. And during her third bout with leukemia, prior to the chemotherapy and radiation, she had her right ovary removed. And it was removed and then cryopreserved. Of course, cryopreserved is a big word for frozen. And so why did she do that? Well, the cancer therapy, the chemotherapy, the radiation what it would have done is it would have essentially wiped out her ovaries. Now, they would have quit functioning. She would have become infertile. She would have been unable to have any children. And so what they did was they removed the ovary, froze it with the idea that okay, we'll take it out, we'll preserve it, then we'll apply the cancer therapy, and then when she recovers, we can we can transplant it back in. Indeed, that's what happened. So when she was 15 years old, it was frozen, it was removed, frozen. She underwent the chemotherapy and radiation. Then she recovered from that. And then about 10 years later, now as she's 26 years old, that cryopreserved, that frozen ovarian tissue was then grafted on to her remaining left ovary, which indeed was at that time it was menopausal. Okay, because of the cancer treatment, she then quit cycling and she was infertile, and so they put that frozen ovarian tissue back in. And then now here's the amazing thing. They put it back in and she started cycling again and she became fertile again. And then I'm happy to show you this picture. This is Elise's daughter who was born in 2020. And so this is a nice picture of them together. And so for me, this is just completely amazing, right? Without this procedure, this beautiful little girl would never have been born. And the so this when I first heard about this procedure, I thought it was really amazing. And so this is a typical use case for Elise Starling. This is kind of a schematic diagram of how this procedure is applied. So typically you have a young woman diagnosed with cancer, and then she has some of her ovarian tissue removed and then cryopreserved. Then she undergoes the cancer treatment, she recovers, and then that frozen ovarian tissue is then transplanted back into her. And the amazing thing is that she starts cycling again and she becomes fertile again. And so this was first done by my collaborator in late 1999 and published here in the New England Journal of Medicine. I noticed the first author is this a collaborator of mine, Kutluk Oktay, who I mentioned earlier. So when that was first done, that was the first time it was done. It was an experimental procedure. But since then, this procedure has grown in application. It was accepted by the American Society for Reproductive Medicine. It was accepted as non-experimental back in 2019. And in fact, over 200 babies have been born to women who've had this procedure done. So to me, I think this is just completely amazing, wonderful medical science here. And I can't resist showing you some newspaper headlines back when this was first done. So you notice especially on the right here, this newspaper headline. This is from late 1999. You see the headline, "Menopause is reversed," and there's this little headline here. Maybe you can see it: "Babies for women in late 60s." So the reporters got a little bit too excited there. That has not happened. But I show you these to make the point that when this procedure is really exciting and really opens up the door for a lot of different possibilities. Okay, so what does it have to do with what I want to tell you about today? Well, I'm talking to you about potential ways of delaying menopause. And so I want to show you this headline here. This is from the Wall Street Journal, published a few years ago. You can see the title of the article, "What if we could get rid of menopause?" And the subhead says, "New efforts to boost women's health and extend fertility depend on developing tools to slow the aging of the ovaries." And so this is one headline, but in fact, this a number of there's been a lot of interest in
Hmm.
potentially delaying menopause. Here's a article in the New York Times asking, "Is delaying menopause the key to longevity?" Here is Time Magazine, "Can you actually delay menopause?" And so what all these articles are about is that in the past few years, there's been a huge surge of interest and indeed financial investment in finding and developing therapies, ways of delaying menopause.
Mm.
And some of the motivation is fertility, but the primary motivation is for extending and improving women's health. So
Hmm.
there's a number of lines of evidence which suggests that at menopause, women's health declines in terms of bone density and risk for obesity and cardiovascular disease and things like this. And so the thought is that if menopause can be delayed, and another way of saying that is delaying menopause is extending the functioning of the ovaries, right? So make this organ continue to function longer. The thought is if you can do that, then you can improve women's health. And so there's lots of interest in doing this. Most of the therapies which people are working on are pharmaceutical, so they're
Mhm.
trying to come up with drugs which slow the aging of the ovaries. But there, ever since, I was telling you about ovarian tissue cryopreservation, and that's always been done for cancer patients. But ever since that was first developed, there's been interest in potentially developing it as what you could call an elective procedure as a way to delay menopause. So let me tell you about that. Um, so the schematic diagram for ovarian tissue cryopreservation as a way to delay menopause is just like before, except for there's
Mhm.
no cancer. The woman is otherwise is healthy. So the idea is you have a woman who decides that she wants to effectively bank some of her ovarian tissue, so she has it removed and then cryopreserved. It's frozen, and then she undergoes aging as she otherwise would. So the years go by, and then some number of years later that ovarian tissue is then transplanted back into her. And then the idea is that that might delay menopause. The idea being that you're effectively taking some, younger version of the ovaries and putting it back in. It's like you could, as an older individual, you could have, a younger version of your organs, and that's the idea. And this is how I got involved in the project. So I had been working with Joshua Johnson, modeling ovarian aging for a couple of years, and then Kutluk Oktay, the surgeon I mentioned earlier, reached out to our group and asked if we could use our mathematical models to study this procedure. And so, let me now list some of the questions we're trying to answer. So the first question, if people are really interested in seriously doing this procedure as a way to delay menopause. But if you're going to do that, first you have to ask the question, is it going to delay menopause and by how much?
Mhm.
Right? You could imagine if it's going to delay menopause by a few months, then no one is going to be interested in doing it.
Mhm.
But on the other hand, if you could delay menopause by 10 years or
Mhm.
20 years,
Mhm.
maybe there's more interest in doing it. So that's the first question. Can we quantify, can we predict what the delay in menopause is?
Mhm.
And then there's a number of questions which relate to you could think about as optimization. So how much ovarian tissue should you remove?
Mhm.
It's clear that if you don't remove enough, then you're not gonna it's not going to matter much. You're not going to delay menopause very much. On the other hand, if you take out too much, maybe you have not left enough in there to keep cycles going, and maybe you're going to have to put it back in very soon. And so the question is there some optimal amount to remove? When should you remove it? Is there an optimal time, or is there an age at which it's too late? When do you return it? And then what about the effect of follicle loss? So I haven't said anything about follicles. I'll tell you about follicles in a moment, but for now, the follicles are the structures in the ovaries which become eggs. And right now, the state of the art for this ovarian tissue cryopreservation procedure, as it's been done in cancer patients, is about only about 40% of follicles survive this procedure. That is, if ovarian tissue is removed, frozen, and then transplanted back in later, about 40% of the follicles, or you could think of the eggs, which are in that ovarian tissue, survive that procedure. And so one would like to quantify how does that follicle loss affect the delay in menopause? And there's a lot of research and work trying to improve that survival percentage. And then the last point is, I think, a really nice idea. What about multiple returns? So this was my collaborator Kutluk's idea based on his clinical experience that so suppose you remove some of the ovarian tissue, instead of putting it all back in at once, perhaps you could put in a half of it back in, and then some number of years later you put in the other half, or maybe you put it back in once, a third, and then another third, and then another third. Is that a way to further delay menopause? And so I would like now just to kind of pause on this slide and go back to my main point I mentioned on my first slide is that mathematical modeling is a uniquely powerful tool to answer questions in physiology and here in medicine. So here are some pressing medical questions. This is a real procedure. People are really interested and want to do this as a way to delay menopause, but there's all these questions. Is it going to work? How much?
Mm-hmm.
How much are you going to delay menopause? How much should you remove? When should you put it back in? All these questions. And these are questions which, it's not certainly not practical and not easy to investigate with clinical trials or, these other means. And, it's not like something we can just feed into a big machine learning algorithm either, because we don't have a lot of data on these things. And so how are we going to answer these questions? Well, this is where I think mathematical modeling is a help, can provide some kind of guidance here. So with that, let me tell you a little bit about our models and some of our predictions for these questions. So in order to tell you about the models, I have to tell you a little bit about some basics about ovarian aging. And so this cartoon on the left here, all these little circles are meant to represent dormant primordial follicles. So these, again, follicles are the structures in the ovaries which become eggs. And so they what happens is they lie dormant in the
Mm-hmm.
ovaries for years and
Mm-hmm.
years, but then every once in a while they wake up
Mm-hmm.
and begin to grow. So let me tell you a little bit more about this. So a woman is born with, I'll say, capital N, many of these follicles, and capital N, the number of follicles a woman is born with varies by about an order of magnitude between women. It's typically around 10 to the 5 to 10 to the 6. So, hundreds of thousands to maybe a few million. Um, and so now, what we want to do is we want to introduce some modeling here. So what I'm going to do is I'm going to index those follicles by 1 all the way up to capital N. And then I'm going to let these letters here, tau 1, tau 2, all the way up to tau sub n, be the times that the follicles leave the ovarian reserve. So that is, these are the times that individual follicles wake up and begin to grow. And so on this cartoon at the left, you see of this follicle here, it was dormant until the woman was 19 years old, and then it began to grow. And this one when she was 31, and then this one, 16 years later when she was 47. One thing I think which is so amazing about this system is you have these follicles lying there dormant for years and years and decades, and then all of a sudden they just begin to grow. And then so in particular you can have a follicle you know in the ovaries which is dormant until a woman is 19 years old, and then you have a nearby follicle which lies there dormant for another 12 years until she's 31. Um, and so a big question in this field is why do follicles begin to grow at the particular time they begin to grow, right? Why does one grow when she's 19 and one when she's 31 and so on? Um, well, yeah, so I should tell you one more thing. So how do follicles relate to menopause? Well, right now the textbook understanding for menopause is that menopause occurs when the number of follicles dips below a critical threshold. I'll call that threshold K, and it's around 10 to the 3. It's around 1,000. So the picture you should have in your mind is that a woman is born with around 1 million follicles. And then over her lifetime, the follicles leave dormancy to begin to grow, and so the
Mm-hmm.
size of the ovarian reserve decays
Mm-hmm.
until you only have about 1,000 left, and that's
Right.
when menopause happens. And the average age for menopause is around age 50, but it varies between in the 40s to even early 60s.
So that means around 1%, less than 1% is left, right?
Yes, yes.
Oh.
That's right. Yes, and that actually that will be important in a moment.
Mm.
But you're right to do that math. And maybe I'll say one more thing about that.
Mm.
Uh, there's an interesting question which we've done some work on. I'm not planning to talk much about today, but if you can do some quick math and you say, okay, well, a woman typically ovulates 1 egg per month.
Oh, yes.
And, there's usually around, maybe a woman has around, on average, 40 years of menstrual cycles. So
Mm-hmm.
you do some quick math. You say 12 months in a year, 12 times 40 gives you 480. So that means, on average, typically a woman is going to ovulate around 500 eggs in her lifetime.
Mm-hmm.
But yet you look up here and you see that she's
Yeah.
born with, up around 1 million.
Yeah.
And so this is actually there's this uh, big question of oversupply or redundancy. In fact,
Hmm.
you can look in physiology textbooks and they describe this as a wasteful oversupply, that there's,
Yes.
1,000 times too many of these follicles or 1,000 times too many eggs. And so we've done there's some interesting questions there about why that could be physiology beneficial.
Mm.
Okay, but let me keep talking to you about these follicles. So. Uh, I won't go into the details of the model, but the important thing for our purposes is that these taus, that is, these follicle growth times, they've been modeled as random since going back to the 1970s. And so I list here a number of papers. We did some work in 2022 on this, but this work goes back to the 1970s, and I've bolded the last author here, Edwards, on these 1976 and 1983 references because this Edwards is Robert G. Edwards, the Nobel Prize winner he won the Nobel Prize for inventing in vitro fertilization.
Mm.
So that's just to make the point that this understanding follicle growth times as random
Mm.
is a very mainstream way of understanding
Hmm.
ovarian aging, going back to people who won the Nobel Prize for in vitro fertilization. And then this actually, so Jay's already ahead of me here. He figured this out already. That
Mm.
menopause time is then an extreme statistic in
Mm.
the sense that suppose if you have 1 million follicles at
Yeah.
birth,
Hmm.
and then menopause happens when you only have 1,000 left. And so that means that menopause is controlled by the thousandth slowest out of 1 million. So this is sort of,
Mm.
the 0.1% slowest follicles out of the million follicles. So these are rare events or extreme outliers. And so that's kind of the mathematical tool,
Mm.
the key to the work we've done on this. And I won't say much more about that, but if you uh, that's kind of the mathematics that's doing the work here is the theory
Mhm.
of extreme statistics. Okay, but let me tell you in a quick slide the idea of the modeling and how we try to predict menopause delay from ovarian tissue cryopreservation. So here's a schematic. Here's a graph of a woman's primordial follicle count over her age. And you see the gray curve is you can see she's born with a few 100,000,
Mm.
and then over her lifetime, her ovarian reserve, the follicle count decays, 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 and
Mm.
then when it hits that horizontal dash line of a
Mm.
thousand, that's when menopause happens. And so you see for this woman, the gray curve, she has menopause right around age 51, which is
Uh-huh.
the population median. Right now, the blue curve
Mhm.
is a model's prediction for what would happen if you remove some ovarian tissue.
Mhm.
So in this graph, when she's at age 30, some ovarian tissue is removed, and so you see the follicle count drops down, and then it decays, decays, decays as normal. She ages, 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 and then just before she would hit that menopause threshold, the ovarian tissue which was removed is then put back in. So then the follicle count jumps up. And I'll just point out here, I'll emphasize that the vertical axis is on a log scale. So it looks like we're putting back in more than we took out just because of the log scale, but we're not doing that. That's just a distortion of the log scale. So it's put back in at, say, around age 49, and then she ages as she otherwise would. And then in this graph, the
Mm.
prediction is that she would have menopause here. Looks like around age 62.
Mm.
So then the primary way we describe the efficacy of this procedure is in terms of the menopause delay. And so what we do is we say, well, for this woman, if she did not have this procedure, she would have had menopause at age 51. Now with the procedure, she has menopause at age 62. And so the predicted delay is 62 minus 51, it's 11 years. But of course, this is one particular woman, and I and one particular woman that we're modeling. But I mentioned that the follicle count she's born with here at age 0 that varies quite a lot between women, right around an order of magnitude. And of course, you could have taken out the tissue at a different age. You could have taken out a different amount, and all kinds of things. And so this is just one specific example to illustrate the idea, but. Here is a mathematical formula we worked out. So this is using our model of ovarian aging. And
Mm.
then with that model of ovarian aging, this is the predicted menopause delay. And I won't talk through the specifics of the formula, but I'll just mention, what does this formula depend on? It depends on the things you would expect. P is the proportion you remove. So what percentage of the ovarian tissue are you removing? So that's, from the standpoint of the surgery, clinical standpoint, that's known. Little t zero, that's how old the woman is when the tissue is removed. So we know that. Capital T zero, that's the menopause age without the procedure. Now, of course, we don't know that. So if a woman is 30 years old, she has the procedure done, we do not know when she would have had menopause without the procedure. However, we do know very well how this menopause age varies across a population. And so we can use that data there. And then the other parameters are S is the survival proportion. So I mentioned that right now the state of the art is maybe only around 40% of follicles survive this procedure. So it depends on that. Lambda is the decay rate. So this is the rate of follicle decay. This is kind of like a rate of ovarian aging. We can estimate that based on data on follicle counts from different women. And then the last variable, capital R, is the number of returns. So I mentioned that rather than putting all the ovarian tissue back in at once, like we do in this graph, perhaps only you put in half of it in, and then a few years later you put in the other half, for example. And so this is all these are what the menopause delay depends upon. And then let me show you, I hope this works. Uh, this is, so one thing on this project, that has been a challenge is trying to communicate mathematics to a clinical audience. And, so clinical audience is not used to looking at a formula like this. And so we put together a little online calculator. Can you see this website? Is it showing up?
Mm-hmm.
Okay, great. So this is our collaborator Look's clinical website. And so we put together a little
Mm-hmm.
calculator here. And so you can change the woman's age at removal. So let me just show you an example. Suppose that we have a young woman who does this, maybe she's 21, and then the percentage of the ovarian cortex which is removed, suppose 50% is removed. So that's one ovary. And then right now, let's say the state of the art is only 40% of the follicles survive. And let's say instead of putting it all back in at once, maybe you put it back in at thirds. And so here at the right, if you can read this, this is predicted some predictions for the menopause delay, and there's some uncertainty here, but the mathematics predicts in such a scenario, you're going to delay menopause by a few decades.
Mm.
And in fact, if tip average age of menopause is age 51, and so if you delayed it by 40 years, now you're
Mm.
having menopause at age 90, you're past the typical life expectancy. So in that
Mm-hmm.
way, menopause has in fact been eliminated. Okay, so that's um, so
I see.
that's the
So
first
that
project
that
I wanted to
website
tell
is
you about.
based on this simple formula.
Yes, yes,
Okay.
yes. Yep.
Oh,
Yeah.
but
So
it's a
okay, so
very
that
recent one, 2024.
oh yeah,
Okay.
yeah,
Okay.
yeah, yeah, yeah. Yeah, okay, so that's the first project I tell you about. Again, the big idea I wanted to argue that the
Mm-hmm.
mathematics is a useful tool for answering questions in physiology and specifically medicine. So that's project number one. Let me tell you about another very different application, very different problem, but I hope you'll agree. I hope I can convince you that the
Mm-hmm.
mathematics is useful here. So the
Mm-hmm.
second project is medication non-adherence, and this is
Okay.
work that I've done with a PhD student, Eli Clark, who's since graduated, some undergraduates who've also graduated now, and then Ray Tung, who's an awesome postdoc,
Yes.
just finished and is starting a faculty position at Texas A&M
Mm.
next year. And so let me tell you about medication non-adherence, and to tell you about medication non-adherence, I need to tell you about medication adherence. So, medication adherence is the extent to which patients take their medications as prescribed. And it turns out that medication non-adherence is a huge problem. And so you can search on Google or ask ChatGPT and find out lots of different scary statistics. And so here are a few. It's estimated that over 100,000 deaths every year are caused by medication non-adherence and over $100 billion in healthcare costs in the United States. And these are certainly worldwide problems as well. Um, Here actually is a quote which I think illustrates the problem even better than the statistics. So the World Health Organization has said that Increasing the effectiveness of adherence interventions may have a far greater impact on the health of the population than any improvement in specific medical treatments. So, what are they saying? They're saying that if we could just get people to take the medications that we already have, if we could get them to take those as they should, that would improve public health more than inventing new medications and new treatments, right? Which is completely an amazing statement, right? I mean, think about all the research, all the work that comes up that goes into trying to come up with new therapies. They're saying that if we could just take the therapies we already have and we could take those properly, that would improve public health more.
Mm.
Like, let me give you two more quotes. This next one, I like this one. Even I can understand this. Former United States Surgeon General said, drugs don't work in patients who don't take them. Well, this is a pretty simple idea. If you don't take it, it's not going to work. And then this last quote, I like. This shows that medication non-adherence is a very old problem. So Hippocrates, the father of, so-called father of medicine back in 400 BC, said, keep watch on the fault of patients, which makes them lie about the taking of things prescribed. So apparently, so this tells you medication non-adherence is a big problem, and apparently it's a very old problem, effectively as old as medicine itself. Okay, so so I'm trying to argue that math is really useful for studying this. Why is medication hard to study? Well, first, the think about the ethics of clinical trials. I mean, there's all kinds of ethical issues if you say, okay, we're going to take a population and they have some drug they need to take, and we're going to force them to miss 20% of their doses, and we're going to see what happens. Right? There's problems here.
Mm.
The second thing is, I wrote here many parameters and different drugs. Another way to say that is, different drugs are different. So even if you understand the effects of medication non-adherence very well for one specific drug, it's hard to extrapolate that to other drugs. And then the last point, patient non-adherence is erratic. So this is
Mm.
it's by nature erratic. It's not like you miss doses on some perfect predictable pattern, right? It's not every Thursday you miss your dose. It's sometimes you miss it, sometimes you take it late, right? And so I think actually for all these three reasons, math is very useful. So first of all, for clinical, there's no ethical considerations in mathematical modeling in terms of missed doses. And then, lots of different drugs, but in different parameters, but as applied mathematicians, that's what we're good at. We're good at varying parameters and investigating the effects of that. And then last, patient non-adherence is erratic, and so what we do is we model this by a stochastic process. So our basic approach here is we take a pharmacokinetic or pharmacodynamic model. So this is a mathematical model of how a drug moves through the body or how it affects the body. And that's a deterministic model. There's no randomness there. But then we model the drug taking behavior by the patient as a stochastic process. Maybe the simplest model is every time they're supposed to take a dose, they flip a coin, and with some probability they remember and they take it, and some probability they don't. So from a mathematical standpoint, one wants to understand how that stochastic drug input propagates through the deterministic pharmacodynamic and pharmacokinetic system. And then, I'll just say from a mathematician's perspective, a bonus here, and this is something I really like, is that there's an existing library of
Mm.
very well-established pharmacokinetic and pharmacodynamic models. So I think I probably don't have to tell the audience here
Mm.
that a big pain, a big problem when doing, a big difficulty in doing any applied mathematics, maybe especially mathematical biology, is building models, is choosing parameters, right? You write down a model, you got some system of differential equations, and you have all these parameters, and how do you choose them? How can you, know what those constants are? But for us, for our approach here is, this pharmacokinetic and pharmacodynamic modeling is a huge industry. And so essentially any common drug you can look up and you can find published models which have been validated to data in real patients. And so our approach is we take these pharmacokinetic, pharmacodynamic models effectively off the shelf. We take those and then we put in this random drug input and we analyze that. And then last point from from the perspective of a mathematician, the analysis of these turns out to be very quite interesting from a mathematical perspective, and I hope to be able to illustrate that a little bit today. And so yeah, so what I want to do is I want to demonstrate these points, and I'll do it in what I'll call three short case studies. And the first two will be very short, and then I'll spend more time on the third. Um, okay, so let me jump into the first case study. First case study is around this idea of drug forgiveness. So the idea of drug forgiveness is that some drugs are said to be forgiving of non-adherence in the sense that for some drugs you can miss doses, you can take doses late, and the therapeutic benefit does not go down very much. So maybe you only take 80% of your doses, but you still get 95% of the benefits. That would be a very forgiving drug. On the other hand, it's very well known and established that some drugs are not forgiving. So there's some drugs, as soon as you miss just a few doses, the
Mm,
therapeutic benefit, the efficacy goes way down. And so one wants to be able to understand what makes a forgiving drug forgiving. How can you predict if a drug is more or less forgiving? How can you investigate that? And so I'll just real quick put just some pictures here. This is some work we've done on this question.
mm,
Here the drug is semaglutide or semaglutide. This you might know more as a popular name Ozempic or Wegovy,
mhm,
a very popular weight loss drug. And so this schematic I hope illustrates our idea. So here at the left, this is the you would call a pharmacokinetic model. So this is the drug concentration over time. And the red curve, this is the red curve is the perfect patient. They never miss any doses. They take it just as
mm,
they should. And so this is what the drug concentration looks like. And then the blue curve is a stochastic simulation. We just take the existing pharmacokinetic model, um, and then we in this model we had the patient randomly miss 20% of their doses.
mm,
Okay, and so you have this erratic, random drug concentration. But then here at the right, this is the results of the pharmacodynamic model, and this is the change in body weight. So this is a someone who's taking this drug for obesity, and you see the red curve. This is the perfect patient. They lose about 17% of their body weight. But then the patient who missed doses, they still lose quite a lot of body weight. They still lose looks like around 16%. And so the point is that even though the patient is only taking 80% of their doses, they're actually getting about 90 something percent of the weight loss. And so that's one example. And then here are some graphs here. Maybe I'll zero in. I'll focus on this right graph here. These are semaglutide. This is Ozempic.
mm,
Tirzepatide is Zep, often called is brand name Zepbound. Uh, and what we do here we're plotting as a the relative weight loss compared to perfect
mm,
adherence as a function of the proportion of doses taken. And so
mm,
the linear the black
mm,
dash line is what you would naively expect, right? You would think,
mhm,
okay, if I take
mhm,
50% of my doses, I'm going to lose 50% of the weight. But
mhm,
what the modeling says, no, in fact, is even if you only take 50%, you're still going to lose about maybe 70% of the weight you otherwise would have. And so this is uh, using mathematical modeling to predict the how forgiving these drugs are. Um, so that's sort of my brief case study number one. Case study number, oh yeah, and this is similar idea. We've done similar analysis comparing. These are some different drugs for treating high blood pressure and showing how, some drugs are very forgiving and then some drugs are very not. And so this is a similar idea. Maybe for time, I'll skip that. Another area where we're using mathematical modeling and medication adherence is designing drug regimens. I'll illustrate this with just one quick picture. And so these are some example, plots for this is an anti-epilepsy medication. So this is an anti-seizure medication. And what I'm plotting here are different patients taking different versions of the drug, either
mhm,
what's called immediate release or extended release,
mhm,
and then taking them at different dosing intervals. And so this is actually a
mhm,
big uh, question in the epilepsy literature because medication adherence is a big problem for epilepsy because for someone with epilepsy, if they miss a dose, they're more likely to have a seizure.
Mm.
So there's a lot of arguments in the epilepsy literature where different groups are
Ah.
arguing different things. So some
Mm.
would say, oh, you should dose only once per day because if you dose once per day, patient is more likely to take it. And
Mm.
then some other groups say, no, you should dose 3 times per day because
Mm.
even if you miss some of them, you might miss more doses because you're doing it 3 times. But if you miss one, it's not as bad because you have another one scheduled soon. Um, and those are just verbal arguments. And what I would argue is that instead you can use mathematics to quantify these, right? So there's different competing effects if you dose more frequently or less frequently or different versions of the drug. And this is just kind of a quick graph to illustrate those ideas. Okay, now case study number three. This is the one I really want to spend some time on, and I'll finish with this. This is one
Mm.
this is the kind of the first thing I worked on in this area, which I um, really found really fascinating. So the question at the top of the slide, what should you do if you miss a dose?
Mm.
And so this is, I think, a very common practical question.
Mhm.
The scenario is, suppose you're supposed to take a drug every
Mm.
day. Maybe you wake up this morning and you realize, oops, I forgot to take my dose yesterday.
Mm.
So what can you do, right? You effectively you can either skip the missed dose, that is, you just take one today. You skip your one from yesterday. You say, I didn't take it yesterday, too bad. I'll just take one today. Or you could say, oh, I missed my dose yesterday, so I'll take two today, right? So you either take a single dose or a double dose. And so when I first started thinking about this question, I thought, oh, this is so practical. Everyone has experienced this. Surely people have thought very carefully about this, and there's a lot of work on it. In fact, very little had been done on it. And so I'll tell you about how
Mm.
our approach to this problem in this last few minutes.
Mhm.
Okay, so we've looked at this question in a number of different, for different drugs and different scenarios. I'll tell you about the simplest possible model.
Mhm.
Okay, so this is what's called a single compartment pharmacokinetic model. This is like chapter one in any
Mhm.
pharmacokinetic textbook. Suppose a patient is supposed to take a dose of drug. I'll just scale my units, so that's just one dose of size one every tau units of time. So if you're supposed to take it every day, tau is 24 hours. Okay, and the other parameter is I'm going to suppose that the amount of drug in the body decreases exponentially, has some half-life, I'll call it T half. Okay, and then so the two parameters in the problem right now, the dosing interval, that is how often you take it, the time between doses, and then the half-life, how fast it decays. I'll put those two parameters together into a parameter I'll call alpha, 2 to the minus tau over t half. The important thing is that alpha is the fraction of a dose that remains in your body after time tau. So if I take a dose right now, then tau units of time in the future, I will have alpha of that dose left in my body, right? So if alpha is 70%, that means, if alpha is 70% and tau is 24 hours, that means if I take a dose right now, then 24 hours from now, I'll have 70% of that dose still in my body. Okay. And then, okay, so now let's think about the perfect patient. So the perfect patient is the patient who never misses any doses. So how much is drug is in their body? Well, immediately after they take their first dose, you know, they have just one dose in their body. And then immediately after they take their second dose, how much do they have?
Mhm.
Well, they have alpha remaining of the first dose
Mhm.
plus the dose they just took. And you can probably see where this is going. So after the third dose, how much is in their body? They have alpha squared
Mhm.
of the first dose left. The second
Mhm.
dose, they just have alpha left, and they have one of the dose they just took.
Mhm.
And so if it's a long-term pharmacotherapy, it's a drug you're taking for a long time, then after many
Mhm.
doses, we know
Geometric.
from calculus, this is a
Mm.
geometric series.
Mm.
I have 1 over 1 minus alpha. And
Mm. Mm.
I'll call this amount, I'll call it A, capital A for amount, and perf for the perfect patient. This is the patient who never misses doses. Okay, so now I need to introduce a model for a patient who sometimes forgets to take a
Mm.
dose. And this is, the simplest possible model.
Mhm.
So what I'm going to do is I'm just going to say at every dosing time, a patient flips a coin. So with some probability P, they remember. And if they remember at the dosing time N, I'll write Xc sub N as 1.
Yeah.
And with probability 1 minus P, they forget. And they forget at dosing time N, I'll write Xc sub N as 0. And so what I want to, so, okay, how much is in their drug? How much is in their body after a long time? Well, if F sub N is the amount they take at the nth dosing time, then the amount of the body is now this random variable. What is it? It's F sub 0 plus alpha F minus 1 and so on. It's convenient to index going backward in time. So we
Mm-hmm.
think about time, the present time is time 0, and then the negative times is in the past.
I see.
And so what you see mathematically, what do we have? We have a geometric series, but now the coefficients are random.
Uh-huh.
Okay, so you remember it randomly, and so you have a random amount in your body. Okay.
Uh-huh. Uh-huh.
The two things I want to compare, I want to compare the single dose and the double dose strategy. So the single dose, this is modeling the patient, who this patient, their doctor says, if you forget if you forget to take a dose, if you miss that is, if you miss your last dose, just skip it. You only ever
Okay.
take a single dose.
Mm-hmm.
So, and then they want to compare that to what I'll call the double dose patient. This is a patient who their doctor says, if you forget your last dose, then you should
Mm.
take two at your next
Mm.
time. Okay. And so I have two different random variables. A single, that's the amount in the single dose patient. It's random. And a double, that's the amount in the double dose patient. That's also random.
Mm.
Okay. So I want to compare those. And so, and this is just, I'll do this real quickly, but just for the mathematicians in the audience, it turns out that these random variables, they seem simple, right? It's just a geometric series with some random coefficients, but actually they're actually quite exotic mathematically. They've been studied in the pure math literature since the 1930s, been studied
Uh-huh.
by people like Paul Erdős here.
Mm.
Um, they were studying them not because they were thinking about medicine, but just because they're interesting mathematically.
Mm-hmm.
So I'll just just for the mathematicians, I'll mention that point. Okay, but back to the application. So I got these three amounts. A perf, that's the amount in the perfect patient. That's where you want to be. That's the amount you want.
Mm-hmm.
We have a single, that's the amount in the patient who they don't, if they miss a dose, just they don't take it. They only take one every time if they remember. And then a double, this is the patient who if they miss a dose and they remember it their next time, then they take two doses. And so what I'm going to do is I'm going to define these what I'll call deviations. So these are just some measure of how far away you are from the perfect patient. So delta single, that's the deviation for the single dose patient. So it's just you take the difference in their amounts, square it, and then take the expectation. So average over all the random remembering and forgetting, and then square root and normalize by a perf. So it's
Mm.
dimensionless. And similarly for delta double. So the point is you want a small deviation because you want your amount to be similar to the perfect patient. Okay, so now I know we just got a little bit of time left, but I'm hoping for some audience participation.
Yeah, please go ahead.
So,
It's okay. Totally fine. Yeah, yeah, yeah.
okay.
Mm-hmm.
Um, so you can find it turns out you can find some explicit formulas for these.
Uh-huh.
And I won't show you all that math, but I'll just, if you want, you can look in the papers, you can work out
Mm-hmm.
formulas for these two
Uh-huh.
deviations. But let me ask you, suppose that the drug half-life is long. So T half
Mm-hmm.
is much longer than tau. So that means your alpha is close to one.
Mm-hmm.
Which one has a smaller deviation? So another way to put it is if you're taking a drug, suppose it's a drug you're supposed to take every day for a long time. Suppose it has a long half-life and you missed your last dose. Should you just take one dose or two? Does anyone, maybe would people be willing to post that in the chat? You can just put a number one or a number two if you'd be so
Uh,
brave. So this is a drug with a long half-life.
mm-hmm. Mm. Let me see what is better. Maybe double? I don't know. Double? Oh no. Wow. Single is better.
Anyone brave enough to want to put, Jay's telling us, anyone want to put a one or a two in there? So
Yeah.
I'll say, I've given this talk before,
Mm-hmm.
and I'll tell you whenever I ask this question,
Mm-hmm.
almost everyone says uh, just take one, but the
Mm-hmm.
math says take two actually.
Oh, yeah.
The double dose is better. And in
Mm.
fact, and which I think is goes against our intuition. In fact, I'll tell you, I talked about this um, about a year ago it was the annual meeting for the International Society for Medication Adherence. So
Mm-hmm.
this is a group of researchers and doctors and pharmacists their whole career they're thinking about medication adherence. And I asked them this question. I said, a drug has a long half-life. You miss your last dose. Should you take one or two? Everyone says one. Everyone's hand goes up for one. And then I try to say, no, actually the math says you should take two. And so
Mm.
now let me try to convince you that the math is
Mm.
right and our intuition is wrong.
Mm-hmm.
And maybe I'll also just quickly say that if the drug has a short half-life, the math says
Mm.
just take one, don't take two.
Mm.
But let me
Oh,
focus on the long half-life for now. So
okay.
maybe for time, I'll skip this. This is about to take it. Is it take? Could you get too much? I could tell you more about that later if there's time. But let me try to argue, try to demonstrate, try to convince you that the math is right in a simple example. Um, I'll do it through the drug called levothyroxine. So levothyroxine is the most common prescription drug in the United States. It kind of varies by year. It's at least top three. And levothyroxine is a synthetic form of thyroid hormone. The brand name is Synthroid. It's a drug for hypothyroid patients. So someone has hypothyroidism if their body does not make enough thyroid hormone. And so the idea is if your body does not make enough thyroid, you just take a synthetic form of thyroid every day for the rest of your life. Okay, so that's certainly a long-term pharmacotherapy, right? And so this is a very common drug. And so, as this very common drug, you can search on the computer, you can ask, levothyroxine, what should I do if I miss a dose? And I would say the standard recommendation is that you should just skip the missed dose. So if you look at places like Mayo Clinic and WebMD and the kind of common mainstream places for health advice, would say if you miss a dose of levothyroxine, just skip it. You should only ever take a single dose. But what does the math say? Well, the half-life of levothyroxine is
Mm.
around 9 days, which is much
Mm.
longer than the
Longer.
dosing interval of 1 day. So the alpha
Mm.
is about 0.93. So
Mm.
the model would say that actually you should take a double dose after a missed dose. And at worst, you can only have about 4% more in your body than the perfect patient, right? So people are often worried about, well, if I take two doses, I'll have too much in my body, right?
Yeah.
It's toxic. But in fact, if the drug has a long half-life, um, taking an extra dose actually only puts you slightly more. In this case, it's 4%, very small amount.
But
Okay, so
Sean, isn't it
yes,
oh, I see. You will show it. Okay.
yeah, yeah. So then yeah. So
Mm.
some graphs I think will help. So
Mm.
here is a graph of this black curve. This is the perfect patient. And
Mm.
I have it times zero. They're already in steady state, right? So they start,
Mm.
this is a drug you take for the rest of your life. So they've been taking it for years already. And so this curve looks like what you would expect, right? They take it, it goes up, and then it goes
Mm.
down over the course of the next day, and then the next morning it goes up
Mm.
again, goes
Mm.
just up and down, right? Notice, it goes between 1 and around 0.93, right? I said alpha is
Mm.
0.93. You can
Mm.
sort of see that. I'll just say, I've normalized this vertical axis so that this perfect patient, they start at 1 there after they take a dose. Okay, so now here is just a stochastic simulation.
Mm. Single
This
dose.
is a simulation of what I call the single dose patient, right? This is a patient, they're following the advice that says if you miss a dose, you just skip it, you only ever take one dose. And in this stochastic simulation, this patient, I had them miss 20% or forget to take a dose 20% of the time, which if you look at data on medication adherence, is actually pretty good if you can remember 80% of the time. And then now the blue curve is a stochastic
Wow.
simulation. Exact same patient in the sense they have the exact same random realization of remembering and forgetting, right? It's not
Mm-hmm.
so they're forgetting just as often,
Mm-hmm.
but they're following the advice that if they remember and they miss their last dose, then they take two doses. And
Mm.
the point is to say that, the
Okay.
blue curve is much closer to the
Mm.
black curve, right? And so if the black curve is a perfect patient, that's where you want to be. The blue curve will put you there, will put you much
Mm.
closer.
Mm.
And it's true that the blue curve sometimes goes too high, right? But
Mm.
it's only a few percent compared to
Okay.
the amount that's in your body.
Is
So
it because
that's
half-life is longer?
because the half-life is long. That's
Ah,
exactly
nice. I see.
right. Mhm.
Because people can think that because of long half-life, it could be very highly accumulated, but it's opposite.
That's right. That's right. The idea is that if it has a long half-life, then
Mm.
it
Variation is
builds
very
up in your
small.
body a lot over time. So any
Yeah.
individual dose is a small fraction of what's already
Yeah,
out of your
yeah,
body.
yeah, yeah, yeah. I
Yeah. So
see.
yeah, a little counterintuitive. Yeah. Mhm.
Oh.
Yeah. And then just here's kind of a simulation where you're looking at the probability density of how much is in your body, and
Mm.
this is illustrating the same point. And I think
Mm.
I'm running out of time, and so I'll just
Oh, no, don't worry
oh,
about Sean. Yeah,
okay.
go
Well,
ahead. Yeah, yeah.
I'm just about done. I'll end with this slide. This is, I told you about a specific simple model of just this one
Mm.
compartment model and misses
Mm.
doses, but our approach here is much more general. And here I'm just this is a schematic diagram of maybe a typical pharmacokinetic pharmacodynamic model, right? You have some system of differential equations which describe how the drug moves through the body and how it affects the body. And then our approaches here, we model this drug input as a stochastic process, and then we try to understand how that stochasticity in the drug input propagates through the system,
Mm.
and then we try to use that mathematical analysis to answer questions like what should I do if I miss a dose, or what drug is more forgiving, or
Mm.
should I what's a better dosing regimen, once a day or twice a day, and things like that. And so I'll just quit there, and I'd be more than happy to take any questions.
Oh, wow. Thanks so much, Sean. Yeah, let me stop recording.